Welcome to the Deep Dive. Today we're digging into Retrieval Augmented Generation, or RG for short. Basically, RG is a way to make large language models much more accurate and relevant. It does this by letting them tap into external data sources.
Right.
Think of it like giving a really brilliant mind the exact reference books it needs to give the best possible answer.
That's a perfect way to put it. Large language models are amazing at understanding and generating text, but their knowledge, it's kind of stuck with whatever data they were trained on, and that data gets old, right?
Outdated quickly.
Exactly.
Yeah.
So retrieval augmented generation systems, or RG systems, get around that. They let the models pull in fresh information from outside knowledge bases, like in real time.
Okay.
So our goal today is really to unpack these RG systems. We'll look at the key parts, how you actually build one step by step, the challenges you hit when you try to use them in the real world, and also how you figure out if they're actually working well.
And we've got a bunch of sources for this.
Yeah, we've pulled together quite a bit, some deep articles, some really insightful chats from people actually doing this stuff on Reddit. So we're aiming for a pretty thorough but still accessible look at this really important AI area.
Okay, let's unpack it then. So a really core piece of a RAG system is how it finds the right information to, make its answers better. And that's where vector databases come in, right?
Mm-hmm.
What exactly are they and why are they so crucial for RAG?
Right. So a vector database, at its core, it's a special kind of database. It's built specifically to store information and then find similar information really, really fast based on meaning.
Not just keywords.
No, exactly, not keywords. Think about it like this. Traditional databases have tables, rows, columns. Vector databases store data as these things called high-dimensional vectors. Imagine describing a movie. You've got genre, actors, director, plot points. Each one is like a dimension. Vector databases do something similar with text. They capture tons of these dimensions of meaning. So when you ask a RAG system a question, your question also gets turned into a vector. Then the database finds the stored vectors that are closest to your question's vector. Close means relevant.
Okay. It clears it up. So it's about finding things that mean similar things, the semantics, not just matching words. Now, our Reddit source mentioned a whole load of different vector database options. Can you give us a quick rundown of some of the main ones and what makes them different?
Yeah, definitely. The discussion highlighted quite a range, each with its own pros and cons. Pinecone, for example, that's a big one. It's private, cloud-based, pretty popular.
Yeah, okay.
Then there's PG Vector. Now, this one's interesting if you're already using PostgreSQL. It's an extension, so you can add vector search right into your existing PostgreSQL database. Super convenient, yeah. But one person in the thread compared it to PostGIS for geographic stuff. It works, it's familiar if you're in that world, but maybe it doesn't have all the bells and whistles of a database built just for vectors. And there was a note about a potential limit on vector dimensions, maybe around 2000.
So good for convenience, maybe not for the absolute cutting edge or super complex vectors.
Potentially, yeah. It might lack some advanced features, depends on your needs.
Gotcha. What else came up?
Well, FACE was mentioned. Important point here. FACE is actually a library, not a full database. It's super efficient for similarity search, but you have to manage the storage and everything else around it.
Okay, so more hands-on.
Right. Then there's Milvus, that's open source, focused on similarity search for vectors. And they have a hosted cloud version, too, called Zillus, which is aimed at production and, really big data sets. Weaviate and Qdrant also came up both open source vector databases. Weaviate's written in Go, Qdrant's in Rust. Qdrant got a specific mention for being designed kind of with RAG and AI workflows in mind. Apparently has some advanced filtering features, like for multi-tenancy.
Okay, so Qdrant sounds like it's really targeting this RAG space specifically.
Yeah.
Any others worth mentioning?
Yeah, a few more. Chroma was there, another vector database. SembaDB got highlighted because it's simple, straightforward HTTP API, easy-to-read Go code.
HTTP API, that's Hypertext Transfer Protocol Application Programming Interface.
That's the one. MariaDB, which is a traditional SQL database, now has vector capabilities too. So again, useful if you're already using MariaDB or MySQL.
Structured query language, SQL.
Yeah.
Seems like a trend. Existing databases adding vector features.
It does. OpenSearch also has vector search, though the feeling seemed to be that dedicated vector databases might perform better or have more features. Cassandra and Aerospike were mentioned too. Aerospike specifically in relation to GraphRAG, which is a whole other interesting area.
Wow. Okay. Lots of options. It really sounds like there's no single best one then. What was the main takeaway from the Reddit discussion on how to choose?
Yeah, exactly. No silver bullet. The big takeaway was It totally depends on your specific needs. Are you looking for cloud or self-hosted, open source or private? What's your existing tech stack look like? Do you need features like SQL integration? How much data do you have now? How much will you have later? What are your latency needs? How often does your data change? All these things matter.
Makes sense.
There's even a good practical tip. Maybe start with phase, just to get your head around the core concepts of vector search before you commit to a big, full-featured database. So it's not about finding the best database overall, it's about finding the right one for your situation, matching the tool to the task.
Right. Understand the fundamentals first. Good advice. Okay, so you've got your documents. You need to put them in one of these vector databases. But first, you need to turn the text into those searchable vectors. That's where embedding models come in, right? What exactly do they do?
Precisely. An embedding model is basically a translator. It takes text words, sentences, paragraphs, and converts it into a numerical representation, that dense vector in that high dimensional space we talked about. And the critical part is this translation captures the meaning, the semantics of the text. So bits of text that mean similar things end up with vectors that are close together in this vector space. That's the magic that lets the database find relevant stuff based on meaning, not just keywords.
Got it. Our Pinecone article mentioned a lot of people use OpenAI's Ada0002 model for this. Why was it so popular, and are there better options now?
Yeah, Ada002 got really popular early on. OpenAI made a pretty solid, easy-to-use embedding model quite early in the game. But like the article points out, and if you look at the MTB leaderboards, that's the Massive Text Embedding Benchmark hosted by Hugging Face, Ada002, isn't really the top performer anymore in terms of pure accuracy.
MTB, Massive Text Embedding Benchmark. Okay.
But a word of caution on those leaderboards. The results can be self-reported, and sometimes models might be tweaked specifically to do well on those benchmarks. So you can't just look at the score and assume it's the best for your specific data.
Right. Benchmarks aren't everything. So besides the scores, what else should we look at when picking an embedding model?
The Pinecone article flagged a few key things. First, the average score, the retrieval average score on MTE, gives you a general idea of performance. Second is sequence length. That's how much text, usually in tokens, the model can handle in one go to make a single embedding.
Tokens being like words or parts of words.
Roughly, yeah. And the point was, embedding huge chunks, like more than a decent-sized paragraph, say around 512 tokens, often isn't great. It can kind of dilute the meaning.
Okay.
And third is model size. This tells you how much computing power, memory, etc. you'll need to run it. The good news is even some quite large, powerful models can actually run on regular consumer hardware these days.
Okay, so performance, text length limit, and resource needs. The article compared 3 models using an AI RSIC dataset, Ada002, Cohere Embed v3, and an open source one, E5 Base v2. What did they find?
Right, so they looked at indexing speed, how fast they could create the initial embeddings. Ada002 was the slowest, E5 was fastest in their test, but importantly, they ran it on a GPU, a graphics processing unit.
Which speeds things up a lot.
Hugely. Whereas the OpenAI and Cohere models are API-based, so you don't manage the hardware yourself. Application Programming Interface, API. They also noted vector dimensionality. Ada002 has 1,536 dimensions, Cohere's Embed v3 has 124, and E5 Base v2 has 768.
Fewer dimensions means less storage space, potentially.
Exactly. That could mean lower storage costs, which is definitely something to consider.
Interesting. The article also mentioned an input type parameter for Cohere and using prefixes for E5. What's that about?
Yeah. Both Cohere Embed v3 and E5 Base v2 support something called asymmetric semantic search. This is really useful for R because usually you have a short query from the user and you're searching against much longer documents, right? So this lets you treat the query and the document differently when creating the embedding. The idea is to get more specific, more relevant embeddings for each role. For Cohere, you use that input type parameter, set it to search query for the question or search document for your document text.
Okay.
For E5, you add a little prefix to the text before embedding query for the search query, and passage, which just means a piece of text or document for the stuff you're embedding to be searched. It's like telling the model, this is for searching with, and this is what you're searching in, helps it optimize.
That makes a lot of sense, tuning the embedding for its job. Now, E5 is open source, runs locally. Sounds like it needs a bit more setup than just calling an API.
Oh yeah, definitely. Since you run E5 yourself, you need to install software libraries like PyTorch and transformers from Hugging Face. These are big toolkits for working with machine learning models.
Right.
Then, when you process text, first it gets tokenized, broken into those tokens we mentioned, then it goes into the model. The article also mentioned padding tokens and masking. Padding is basically adding dummy tokens to make all your text sequences the same length for efficient processing. Masking tells the model, hey, ignore the output for these padding tokens so they don't mess up the final embedding quality.
Okay.
And finally, mean pooling. Imagine your paragraph is now a bunch of vectors, one for each token. Mean pooling kind of averages them out to get one single vector that represents the overall meaning of the whole chunk. That's your final embedding for that piece of text.
Definitely more involved than an API call.
Hmm.
So how did these three models actually perform on some example questions in the article, qualitatively?
Yeah, the qualitative results were pretty interesting. It really showed that even good models aren't perfect. For why should I use Llama 2, Ada 002, and the others generally gave relevant info about commercial use, research, performance comparisons. But Cohere's first result was actually about the original Llama, not Llama 2, maybe not specific enough.
Mm-hmm.
And E5, in that case, returned something that looked like garbled text. Not great. Then can you tell me about red teaming for Llama 2? None of them actually found info specifically about red teaming Llama 2, even though the info was supposedly in the dataset.
Oh, really?
Yeah. They all gave general info about red teaming LLMs. Cohere's was maybe the most informative, but still generic. And E5 actually returned something not in English, though it seemed related to red teaming. Weird.
Wow, non-English results. Okay.
Finally, what is the difference between GPT-4 and Llama? Here, all three did pretty well, but Ada 002 and E5 gave the info in a kind of plain text table format. Accurate, but maybe not as easy to read as Cohere's more natural language answer.
So a real mix of results, different levels of relevance, accuracy, even strange outputs. Really highlights why evaluation is so important, which we'll get to. But first, how do you actually break down the original documents into these smaller pieces, the chunks that get embedded? The Multimodal DocDev article stressed how vital good chunking is. Why is it so key?
Absolutely vital, yeah. Good chunking is fundamental because it hits both sides of RNN retrieval and generation. If you break documents into smart, manageable chunks, the system can find the exact bits of info relevant to a query more easily.
Right.
And it helps the language model, too. It gets fed-focused, coherent information, not just huge dumps of text where the relevant part might be buried. Better context leads to better answers.
Okay. The article laid out an 8-step process for chunking. Sounds pretty thorough. Can you walk us through those?
Sure thing. It starts, logically, with document ingestion. Step 1. This is just gathering and organizing your documents, PDFs, Word docs, web pages, whatever. It involves prioritizing, getting rid of duplicates, making sure you have the latest versions, and crucially, collecting metadata like title, author, date. And you have to think about access rights, too.
PDF being portable document format. Okay, get the documents in order. Then,
Step 2 is text extraction, using the right tools to pull the actual text content out of those different formats. You want the main content, maybe things like captions too, and you want to try and keep the structure paragraph breaks, titles, lists. And standardizing the encoding, usually to UTF-8, is key here for consistency. UTF-8 is Unicode Transformation Format 8-bit.
got it. Get the raw text out, keep structure, standard encoding. What's next?
Step 3, text cleaning. This is a big one. Tidying up that extracted text. Removing extra spaces, weird characters, standardizing things like making everything lowercase, handling quotes and numbers consistently, removing boilerplate stuff like all rights reserved or table of contents, fixing spelling errors, maybe anonymizing if needed.
Anonymizing, like removing names.
Exactly, removing personal info. Then more normalization. Expanding contractions, standardizing dates, detecting language if you have multiple languages, breaking text into sentences, and maybe removing irrelevant sections like appendices. It's a lot of prep work.
Definitely sounds like it. Ensuring the text is pristine before the next step, which must be.
Step 4, chunking itself. This is where you actually break the clean text into smaller pieces. Lots of ways to do this. Fixed-size chunks, like 500 tokens each, sentence-based, paragraph-based, or more advanced semantic chunking, which tries to keep related ideas together.
Semantic chunking sounds smart.
It can be. Recursive chunking is another advanced technique. The tricky part is choosing the right size, maybe 100 to 1,000 tokens is typical. You need enough detail, but also enough context. You also have to handle odd cases like really short paragraphs, preserve context maybe by including titles, maintain coherence, don't split sentences badly, and have special rules for things like lists or tables. Each chunk needs a unique ID, and you need to track where it came from.
A real balancing act on the size. Okay, step 5 is overlap. Why overlap the chunks?
Overlap, yeah. Step 5. This means deliberately repeating some content between adjacent chunks, maybe 10–20%. It helps maintain context across chunk boundaries. If an important piece of information gets split, overlap makes it more likely you'll retrieve both relevant parts.
Ah, okay. So it reduces the chance of missing info that falls on a boundary.
Exactly. You can overlap by a number of tokens, or maybe the last sentence, or use a sliding window, but there's a trade-off. More overlap means more storage, more processing. Too much can also be redundant. Common ways are like reusing the last 50 tokens, or the last sentence, or maybe a summary sentence.
Got it. A bit of redundancy for better context retrieval. What's step 6? Metadata.
Metadata. Attaching extra info to each chunk. Like, which document did it come from? Where in the document? When was it created? What section? Author? Topics? This stuff is super useful.
How so?
It helps track where info came from, which is crucial for citing sources or verifying answers. And you can use it to filter or prioritize chunks during retrieval. Only show me chunks from documents published after 2022, for example. You can store it separately or embed it in the chunk, maybe as JSON JavaScript object notation. Just need to standardize it and keep it updated and be careful about sensitive data.
Right. Adds context and filterability. Then step 7 is embedding, which we cover turning text chunks into vectors.
Exactly. Choosing your model, preparing the text, running it through the model, storing the vector with its metadata. Sometimes you might have to split really long chunks if they exceed the model's limit, and consistency is key. You use the same model for everything and check the embedding quality.
And the final step, number 8.
Indexing. Organizing and storing everything, the chunks, the metadata, the embeddings in an efficient structure. This is usually where those vector databases like Pinecone or Weaviate come in. The index needs the vectors, the original text, the metadata. Key things to think about here are scalability, how often you need to update it, query speed and security access control, backups, and regular maintenance and testing are crucial.
Wow, that is a comprehensive process just for preparing the data. The article also mentioned unstructured AI briefly. What's its role here?
Unstructured AI sounds like an ETL layer extract, transform, load specifically for prepping unstructured documents for a RAG. It supports lots of formats beyond just text, like PowerPoint, Excel, CSV, comma-separated values, HTML, hypertext markup language, DOC, DOCX.
Okay.
It apparently offers features like smart chunking, extracting tables and charts, keeping the text hierarchy. The goal seems to be to take all these messy, varied documents and spit out structured JSON text, tables, charts, maybe a CSV Excel with descriptions, and rich metadata, basically making that whole ingestion and prep part easier.
Sounds very useful, streamlining that messy front end. Okay, so we've talked about the components, vector databases, embedding models, chunking. How do we actually put it all together to build a full RAG system? Our Mindy article had a 7-step process for this.
Right, building the whole system. Step 1 is setting up the environment. Choosing your language. Python's common installing libraries like Torch, transformers, datasets. Getting your development setup ready for the computational load, virtual environments. Check in hardware, optimizing.
Okay, the basics.
Step 2 is data preparation. We've covered chunking, but this also includes the initial sourcing of good, relevant, up-to-date data, maybe using something like Hugging Face datasets. Then structuring, pre-processing, cleaning, deduplicating, organizing, and constantly checking if the data is still relevant, foundational stuff.
Right, quality data is crucial. What's next in building the system?
Step 3, building the retriever. This is the part that fetches the relevant documents. The Mindy article suggested starting simple, maybe with a TF-IDF vectorizer. TF-IDF stands for Term Frequency Inverse Document Frequency. They gave a scikit-learn example in Python, how to fit it, convert text to a matrix.
A simpler starting point than neural models.
Yeah, potentially. Then they say explore more advanced stuff like BM25 or neural retrievers. Critically, you need to evaluate the retriever precision, recall, F1 score, and fine-tune it to get better at finding the right docs.
Okay, build and test the retriever. Then step 4.
Developing the generator. This is setting up the large language model GPT, or something from Hugging Face transformers. Then figuring out how to feed it the retrieved documents along with the user's query to get a contextual answer. This involves tweaking parameters like response length, creativity, maybe temperature settings, beam search, even extra training data to boost its abilities.
So retriever finds, generator writes. How do you make them work together smoothly?
That's step 5. Integrating and testing the system. Developing the glue between the retriever and generator, then tons of testing. Hitting the whole system with diverse queries to check both retrieval accuracy and generation quality. It's an iterative process test, find problems, refine, test again.
Build, test, refine. Sounds familiar. What's step 6?
Fine-tuning and optimization, making it better. This could mean fine-tuning the retriever on specific data, supervised learning, or the generator, transfer learning, maybe domain-specific training if needed, all while constantly monitoring metrics, accuracy, quality, user satisfaction to see if your changes are actually helping.
And finally, step 7.
Deploying your RAG system, getting it ready for the real world. Thinking about scalability, can it handle lots of users? Security, server setup, choosing where to deploy cloud, on-premises, the whole operational side.
Right, a whole life cycle. It's an iterative process of building, testing, improving, and finally deploying. Now, once it is running, how do you know if it's actually any good? Our Super Annotate article focused on evaluation.
Yes, and this is super important. The article made a great point. Just looking at benchmark scores for models can be really misleading. Real-world questions and data are often messier, different from clean test sets.
How so?
Subtle differences in how people ask things, domain-specific jargon or acronyms, weird formatting in documents, different ways instructions are phrased. All this can make a system perform much worse in reality than it did on a benchmark. So you need practical, context-aware evaluation.
Okay, so benchmarks aren't enough. What should we be evaluating then?
The article broke it down into 4 key areas. First, document relevance. Did the retriever actually pull documents that answer the question? If not, the generator doesn't stand a chance.
Makes sense. Garbage in, garbage out, basically.
Pretty much. Second, re-ranking improvements. If you use a re-ranker step after the initial retrieval, does it actually make the top results more relevant, or is it just adding complexity? Third, answer accuracy. Does the generated answer actually match the facts in the documents it was given? You need to compare it against ground truth or have experts review it.
And the fourth. Sounds critical.
Absolutely. Hallucination checks.
Big problem.
Especially in important areas like finance or medicine. You have to watch out for the model generating plausible sounding stuff that's just wrong. Stuff that isn't actually in the source documents.
Hallucinations are a huge worry. How do you make sure evaluation is consistent, especially across these different checks?
The key is a uniform grading rubric. Clear, standard rules for judging correctness and spotting hallucinations. Whether humans are evaluating or you're using automated methods, a good rubric ensures everyone's on the same page. It makes it easier to compare different system versions and see where the problems really lie.
A clear rule book for grading. Got it. The article also mentioned pitfalls for each component. What could go wrong?
Well, if your document relevance is consistently bad, maybe the embedding model isn't right for your data or queries. If your re-ranker isn't actually improving things, maybe you need to tweak it or even remove it. And if the language model, LLM itself, is giving wrong answers or hallucinating a lot, you might need to try a different one, like maybe GPT-4 for accuracy. Though you have to think about cost and privacy too.
So evaluation helps pinpoint which part of the RAG pipeline needs fixing. The article mentioned Super Annotate helps with this.
Yeah, it sounds like their platform offers tools specifically for RAG evaluation, helping you test and find the right models, identifying the weak spots in your pipeline, maybe creating better data to improve embeddings, and providing a place for teams to collaborate on annotation and refining the evaluation itself. The goal is to make that whole complex evaluation process smoother and drive continuous improvement.
Okay, a tool to help manage that evaluation complexity. Now, let's switch back to the Reddit thread on RAG in production. It had some interesting real-world perspectives. What were some things that maybe get overlooked in theory but are big deals in practice?
One really striking point was how often monitoring and QA quality assurance get glossed over. The consensus on the thread was strong. You can't do this stuff professionally without solid metrics. You have to track performance.
Makes sense. You need to know if it's working.
Exactly. They recommended a paper, RAG Survey for Standard Evaluation Frameworks. There was also a little side debate on terms like RAG backend front-end. Maybe built time runtime is better since LLM inference usually isn't client-side. But the main point was metrics are essential. Tools like Arise Phoenix and AgentOps were mentioned for monitoring AI agents. It's about treating ARD systems like serious software.
Right, operational rigor, like site reliability engineering or SRE, but for AI.
Kind of, yeah. That comparison came up later regarding hallucination tracking.
The thread also listed the biggest challenges people face building these pipelines. What are the main pain points out there?
Oh, quite a few. Coming up with good evaluations and test sets, that's a big one we just discussed. Reducing hallucinations is still a major challenge. Dealing with the sheer variety of user queries, especially open-ended ones.
Mm-hmm.
handling all the different data sources, PDFs, DOCX, Excel, and their complex layouts with lists, footnotes, diagrams, tables. Finding a chunking strategy that works well for everything is proving tough.
I can imagine.
Parsing image-based PDFs efficiently, managing knowledge that might be outdated or just not curated well, and difficulties processing non-English languages properly for chunking. It's a long list.
Definitely sounds like a lot of practical hurdles.
Yeah.
Did the Reddit discussion offer any solutions or tools people are using to tackle these?
Yeah, there were several suggestions. One idea, convert everything to Markdown first as a common format. For chunking, semantic chunking came up again, maybe adding context from nearby chunks to help with things like pronouns.
Okay.
Using GPU-accelerated vector stores like Milvus for speed. Some people are building custom ingestion and search programs for more control. Query classification, figuring out if a query even needs AG or can be handled differently.
Smart.
Yeah,
Not everything needs the full pipeline.
right. Collecting and analyzing user queries and how the system responds is crucial for understanding what's going on. Experimenting with different chunking methods is key. Tools like LlamaParse for PDF to Markdown were mentioned, though losing layout info is a known issue. For image content, maybe screenshot embeddings using something like Colpoly.
Interesting.
And there was that ongoing debate. Use frameworks like LangChain for speed or build from scratch with tools like pgvector for control. Plus, the challenge of tuning queries to work across all sorts of different documents.
Lots of experimentation, lots of trade-offs. The final point from that production, Fred, was about legality and liability around LLM hallucinations. That sounds pretty serious.
Very serious, especially for businesses.
Mhm.
The discussion noted there aren't specific laws yet, but companies are worried. OpenAI and Anthropic have disclaimers saying outputs might be wrong. The Air Canada chatbot case was mentioned. It gave wrong info on bereavement fares, and the airline had to honor it.
Ouch. Real consequences.
Definitely. There's debate on whether algorithmic info has the same accountability as a human employee's statement, but the trend seems to be towards measuring and monitoring hallucination rates rigorously. Kind of like SRE practices for uptime, but applied to accuracy, trying to minimize the risk.
So manage it like any other business risk, even if the law isn't fully caught up yet. Okay, this has been incredibly comprehensive. If you had to boil it down, what are the key takeaways for listeners trying to get a handle on ARIT?
I think the main thing is that building good ARG is complex. It really involves thinking carefully about every piece of the vector database, the embedding model, how you chunk the documents, how you evaluate it. Each step matters. And while there are tons of tools and techniques out there now, there's no single right answer. The best approach really depends on your specific situation, your use case, your data, what kind of performance you need. It's very context dependent.
Absolutely. And looking ahead, with things moving so fast, it'll be fascinating to see how that balance shifts between easy-to-use frameworks and the control you get building from scratch. What new challenges, what new solutions will pop up as RAG gets built into more and more things. Definitely a space to keep a close eye on.
For sure.
Well, thank you for joining us for this deep dive. We really encourage you to explore the resources and concepts we talked about today.